Okay, the last section for this module or chapter is a variation section, and in this section I want to talk about two types of variation. One is direct variation. Now for a direct variation we say y varies directly as x, and so if we say y varies directly as x, then that implies that y is equal to some constant times x. Now another way to say y varies directly as x is to say y is directly proportional to x. The other thing I want to mention is if we talk about y varying inversely as x, well, if y varies inversely as x, then y equals to a constant divided by x. And in that case we can say y is inversely proportional to x is another way to say that. Okay, so let me start you out with writing some expressions here to represent the following. The distance d varies directly as the illumination L. Okay, so, or I'm not sure if, I guess that's L. Okay, so the d varies directly as illumination L. Well, since d varies directly as L, if we go up here we see direct variation would require that d would equal a constant times L. So we have d equal a constant times L. Now this one says the width is inversely proportional to the square of the area. Now notice this is inversely proportional, so that would mean w is going to equal to the constant divided by the other variable. Now but be careful here because it doesn't say it's inversely proportional to area. It says it's inversely proportional to the square of area. So in that case, w would equal the constant divided by the area squared. And then you can also have what's called joint variation, where you have multiple variables here. Here it says the cost is directly proportional to mass and inversely proportional to time. Well, if cost is directly proportional to mass, then the cost would equal a constant times the mass. But if it's inversely proportional to time, then you would divide that by t for time. So the top shows you the direct variation, and then since you're dividing by t, you get the inverse variation. When solving a variation problem, you generally do two things. The first thing you want to do is find the constant. So let's take a look at a problem here, and I'll find the constant first, then I'll solve the problem. So that constant is actually called the constant of variation. So the maximum speed of a race car is inversely proportional to its mass. So that tells me right away that if I use s for speed, and if it's inversely proportional to the mass, then it's equal to some constant divided by the mass. So now, if we're given any information, we can find the constant. So let's see what we're given. A race car with a mass of 5,000 can travel a top speed of 225. So that tells me that if I put in a speed of 225 for S, then I can put in 5,000 for the mass. And now all I need to do to solve for K is multiply both sides by 5,000. And so I'll get 5,000 times 225 is equal to K, which is 1,125,000. So now that I know my K, I can go back to my original equation here and plug it in here, and that would give me an equation with my K entered. And from that, I can now answer the question that it asks. It says, how fast can a car go that weighs 6,000 pounds? Okay, so I put in 6,000 here for M, and so the speed would be 1,125,000 divided by 6,000, and so the speed would be, if you divide that out on a calculator, you get 187.5, and by the way, that shouldn't be pounds, that should actually be miles per hour. So you get 187.5 miles per hour. Okay? All right. So that's how you solve these. Let's look at another one. Here it says the distance that a searchlight the distance that a searchlight can reach is directly proportional to the square of its intensity. If a searchlight has an intensity of 1,000 lumens, it can reach up to 3,000 feet. And then it says, how far can a searchlight with an intensity of 2,000 lumens reach? And then it asks another question. We'll get to that in a minute. So the distance, so that we use D for distance, since it's directly proportional, it's going to be K times the variable. But let's take a look at the variable again. Directly proportional to the square of intensity. So not just intensity, but square of intensity. So if I use I for intensity, then I'm going to say distance is equal to a constant times I squared. And now I'm going to put in the given information. We know that an intensity, if the intensity is 1,000, that the distance the searchlight can reach is 3,000. So let's put in 3,000 for the distance. Let's put in 1,000 for the intensity. And so I'll get 3,000 equals K times 1,000 squared. So that's going to be K times 1,000,000. So I have, if I divide both sides by 1,000,000 now, I get K equals 3,000 divided by 1,000,000. And in a decimal, that would be 0.003. Okay, so now I can take that. I can take this and plug it back in here for K, right there. And then I get D equals 0.003 times I squared. And now I can answer the questions it asks. It says, how far can a searchlight with an intensity of 2,000 lumens reach? So what they're asking me for is they're asking me for distance given 2,000 lumens for I. So let's put in the 2,000 for I, and so we'll get 0.003 times 2,000 squared, and that'll give me 12,000 feet. Now we can ask a question. We could actually ask a question that asks for the intensity as well. So if we know the distance, so let's say a searchlight can only reach 1,000 feet, then let's find the intensity given the distance. So in that example, we set the distance equal to 1,000 feet, and so we get 1,000 equals to 0.003 I squared. Now, the way we would solve this, first of all, you would divide both sides by 0.003, so we get 1,000 divided by 0.003. But that would only give you I squared. So to get I, you have to take the square root of that. So we take the square root of 1,000 divided by 0.003. And then the calculator told me that that was equivalent to 577.4 lumens. Okay, I think I've got one more here. Here it says the cost, C, is directly proportional to mass and inversely proportional to time. You might remember we had that earlier. So let's take a look at what that would look like. Cost is directly proportional to mass and inversely proportional to time. So cost would equal the constant times mass, but over time. And now let's see what we're given. We know that when cost is $1.50, mass is 3 ounces and time is 5 minutes. So let's put $1.50 in for cost. Let's put 3 in for the mass, 3 ounces for the mass, and let's put 5 minutes in for the time. So we know 1.5 is equal to 3K over 5. Well, if I cross multiply here, let me show you here. Write that as 150 over 1. $1.50 over 1. So if you cross multiply, 1 times 3K would give me 3K, and then 1.5 times 5 would give me 7.5. And then divide both sides by 3, and you get K equals 2.5. So now let's put the K back into our equation up here, and we get, over here we get 2.5 m over T for C. So C equals 2.5 m over T. So now it says find the cost when the mass is 5 ounces and the time is 10 minutes. So we put in a mass of 5 ounces here and a time of 10 minutes here, and we get 2.5 times 5 divided by 10, and that's actually going to be, I think, 12.5 divided by 10, which is actually gives us a cost of $1.25. And so there you have it. There is how you solve variation problems. I wanted to end this with something I ran across. Just wanted to clear up something in case you run across this in a text. Some textbooks teach this a little bit differently. They say if y varies directly as x, then that's the same as saying that the constant is equal to y over x. But if you think about it, if you were to actually solve this for y, you could multiply both sides by x. You would actually get the equation y equals kx, which is actually exactly the equation I have down here. And also in that same vein, they'll say y varies inversely as x. In that case, they'll tell you that the constant is equal to y times x. But again, if you solve that for y, you'll get y equals k divided by x, which is the same thing I have here. So it's really the same definition. It's just stated a different way than I stated. So I just wanted to share that with you in case you ran across a textbook that defined direct variation and inverse variation based on the constant rather than based on the variables like I did here. Okay, that should finish this chapter on rational expressions.